Alright, so let's go for it. Again, ask the questions if you need it here, but we're on 8.2.8, sorry. The basic operations you've seen in Math 63. The composite function you may have not seen, depending how far you got in the book. Then we're going to look at domain of composite functions here, decomposing or the decomposition of a function that you have not seen probably. Then we're going to apply it to some situations here. So let's go for it here. So first things first, whole concept of difference and sum and product and quotient. There it is. You probably have seen before. Whenever you have a function, name of a function called f, name of another function called g in parentheses, and you have x, technically what you're doing is you're adding these two functions together. Again, minus sign, I think you've seen this before, it means you're really subtracting two functions, multiplying two functions, dividing two functions, the quotient rule. Again, that is inside your textbook here. Let me move things around so I see it as well. Alright, and we're on page 258 in your textbook if you got it. Alright, where is this helpful for us is kind of interesting. Whenever you think about even subtracting two functions, if you can figure out two functions, subtract them, what we usually get is we get new information we did not know. So, good example that I usually use, if the f function is our US population, and g is our immigration population, right? We can kind of tell on the border who goes away, we count them. If you subtract the two functions, you get something that you actually is totally different than before. You get technically birth and rate information for just the United States. So yeah, that's totally different. You would not know that from before. It's a totally different concept of data. So kind of important there. Whenever, even in the subtraction of two functions, you get something quite a bit different. Okay, product, of course. If you multiply two things, if you figure out how you can get a function of price and how many you can sell, you can actually get something different called revenue. You can tell how much revenue you're getting. So, anyways, there it is. The example problem. And this one, I'm going to, I guess, set up the example problems as well here, just so you can follow along with me in the textbook here. You can ask any questions of the example problems. Encourage you guys to read ahead with the example problems. Sometimes they're useful here. So we're given two functions here. F of x is x squared minus 6x plus 8. Again, g of x is x minus 2. And then we got to do this stuff here. So notice for this one we're just going to subtract, but we already know the value of it. So if you do that, what you do is you get the value of each one of those. So if you plug in 4 for the f function, you get a value of 0. Plug in a 4 for the g function. So when you do that, all you really have to do is plug in the values and subtract. What gets a little bit more complicated is if they want a general function, like c. I want f plus g of x. In this case, we don't plug in any values. In this case, we plug in just the rule itself, and we simplify it according to our algebra rules. Alright, so let you guys try one here. F of x is 3x minus 1. G of x is x squared plus 2. Can you add the two functions together? Can you subtract the two functions? Give you guys a minute. Try it yourself. At least try the first one, the addition of the two functions. If you got that, do the subtraction. If you look in your textbook, you actually find what other two things you still need to do. So if you want to stay ahead of me, go for it. If you want to stay right along with me. then let's go for it here. So really what this means is I'm adding two functions together. I'm adding the f of x function and the g of x function. And again, because it's just the generalized x as the variable, the rule for f of x is 3x minus 1, adding it with x squared plus 2. And normally when we add functions together, especially polynomials, we write the one with the highest degree on the x first. Is that right? So x squared will go first. Let's see, 3x, there's no like terms to add it with, and a negative 1 and a positive 2 make a plus 1. We're good there. Alright, let's subtract them then. So f of x minus g of x. Again, same exact concept, very similar. We write the rules themselves. This time we have subtraction of the 2. Alright, and I'll let you guys try that real quick here. Hopefully you guys can do that in your head. Should be able to do that in your head. Alright, think of this as subtraction. This is technically a negative x squared and negative 2, so this would be a negative x squared. 3x comes down. In this case, it's a negative 1 subtract a 2, or negative 1 plus a negative 2 makes minus 3 at the end. Cool. Alright, how about multiplication and division between the two functions? And again, give you guys up to a minute here, try it yourself. Cool. Alright, I'm going to try it myself as well here. So this is technically what it's saying is f of x multiplying g of x. The rule for f of x is x minus 1. G of x is x squared minus or plus 2. Man, looks like FOIL method to me, is that right? The first numbers multiplied gives you 3x cubed. Let's see, then a 6x, then a negative x squared, then a minus 2 at the end. And again, you can leave it like that if you like. You can rewrite it in standard form, which means the highest degree goes first, and the degrees go down until you get your constant term or no terms left over. Division, again, f of x goes on top, g of x goes on top, on the bottom, and again, just rewriting f of x, rewriting g of x, and the only thing we would do extra on the homework, if you can somehow factor stuff, and if they do cancel, then give the simplified version. So if you can factor it down, go for it. In this case, can't factor the top, can't factor the bottom, so in this case I'm done. That would be the quotient between the two functions. Okay, so let's see what we got here. We got combining functions, add, subtract, multiply, divide. Now let's take a look at domain. What happens if you add, subtract, multiply, divide functions, but then you're more interested in which numbers work and which numbers don't? Let's take a look at those. So practice problem number 2. let you guys write it down if you need to. Go for it. But the whole concept of domain now, how does that work? Alright, and remember there's two issues to domain. First is a fraction. If you have a fraction, the problem with that is whenever the denominator is equal to 0, that number, whatever makes that, cannot be part of my fraction. The other ones are square roots. Since in calculus we deal with real numbers here, the number right here, x minus 1, that number has to either be 0 or greater than 0. It can't be a negative. So we have a little word in mathematics, we say non-negative number, which means 0 or positive. So what we should start off doing is figure out the domain of each of these here. So the domain for this one is x minus 1 has to be greater than or equal to 0. If I solve it, I get this right here. So for this particular problem, x has to be greater than or equal to 0. Cool. All right, let's solve the other one here. 3 minus x. The domain for this one, or the g function, let's see, I can subtract 3 from both sides. Divide or multiply through by a negative 1. And a big humongous alarm goes off in your head, is that right? Whenever you divide through or multiply through by a negative number, you have to switch the inequality. So the inequality has to be changed because you divided through with a negative 1 or a negative number. Okay, cool. With that said, let's actually just do a quick graph of this one here. The domain for this one, if I were to actually put it on a number line, we would say, let's see, starting at 1 going off to infinity, is that right? In interval notation. Graph-wise, it kind of looks like this. Starting one with a bracket. And again, the graphs are really mostly for you guys to sort of help you visualize the answer here. Alright, and then let's see, the domain of g is x less than or equal to 3, so that means all the way from negative infinity all the way up to positive 3 with a bracket this time. So that means the graph is 3 is sort of on the right hand side of 1, so 3 kind of goes over here. It's a bracket and it goes down this way. Alright, this one you probably can write in here. So for f plus g or f minus g and f times g, and if you were to add, subtract, or multiply, the domain is always just the intersection of the two domains. Remember, intersection is when both of them work, right? So at maybe like x equals negative 5, do both of them work, or are both of them true? Nah. At x equals negative 2, no. At x equals 0, no. At x equals 1, yes, right? It's this interval from 1 to 3 that both of them are true, both of them work. So if I were to add or subtract or multiply, in this case I'm multiplying, if I were to multiply these two functions together, the domain that I can only use is actually from 1 to 3, including 1, including 3. Would not be able to use 4 or 10, negative 7, no way. Can't even use 0. This is really, really restricted. Okay, but the trouble really comes in is whenever you think about these functions and you start dividing things, because now the whole concept of this guy can't be equal to 0 comes in as well. So sort of have two domain problems at the same time. Okay, everybody good there? Are we done with this one? So now practice problem number 2 deals with this one here, f divided by g. What's the domain of this now? What happens if you're dividing by g? How do the things change? So for f divided by g, it is the intersection. There's one little component added, and g cannot equal 0. So it's only one little point that's Alright, so how do we do that? A lot easier just to go back to our original domain. Original domain for f was from 1 to infinity. That a graph looks like this. Original domain for g was from infinity to 3. Graph looked like this. And the only thing we're going to change, we're not going to look at g from equaling 0. We're going to look at g from greater than 0. So let me go back, maybe easier thing right here. So this right here changes into, instead of greater than or equal to 0, this thing changes into just greater than 0, because g is on the denominator.
Can you explain again what a intersection is? Like, does that mean that it can be multiplied, divided, or you know, like, yeah.
Okay. Quick review of intersection is whenever you have two graphs, it's where they both meet together. So if I were to squash this graph on this graph, make a sandwich out of this, this is where they would collide right here. So this would be the intersection of the two graphs. It's where two number lines crunch together and they hit each other. So the intersection here would be from 1 to 3. That's the intersection graph. If you think about it, that's the AND graph from algebra. Whereas this and this true, it's true from 1 to 3. Okay, so really, if we're looking at this correctly, x is less than 3. That's kind of what we're looking at for the g function, because we're changing it up a little bit here. So go back up to here, and the only change is the g function. G function now is infinity to positive 3, now with a parenthesis now. Okay, now with that, can you make an intersection of the two? It's going to be looking very similar to the previous one, except what we're going to do, we're going to start off with 1, but when we get to 3, we got ourselves a parenthesis. That's really the only difference there. So you can't include the 3, then you take off the 3 as an answer. And of course, people that read ahead are saying, oh, I'm so glad I read ahead. This actually makes so much sense now, because I've read ahead. Alright, next one. Let's flip it the other way here. How about if the g is on top and the f is on the bottom? How does the domain... So it's going to be exactly the same. It's still the intersection again, except this time the f cannot be equal to 0. Alright, so going back to my previous graph here, if I want to do it again here, so domain of f, remember originally it was like this. The individual function. The original g function is from negative infinity to 3. There's my original g function domain. Again, give you guys a little bit of time to draw it out if you like. Go for it. The only change is, since f is on the bottom, we can't include the 1. We're not including when it equals 0, so this has a changed from parentheses 1 to infinity, because we're excluding the endpoint this time. Alright, and think about it here, the intersection of this stuff, but now don't include the 1. So in this case, the domain of g over f would be 1 to 3, including just the 3. Again, it's kind of getting a little abstract here, so let me go back to just the function itself. If you think of the function themselves, g on top would be the square root of 3 minus x. F on the bottom would be the function of the square root of x minus 1. So notice, because of this constraint, the highest number I can put in here is 3. Because this constraint, the lowest number I can put in here is, I can't put a 1 anymore, because 1 subtract 1 is a 0, and square root of 0 is going to be 0, and that's going to be a problem. So the lowest number I can put in here is something a little bit bigger than 1. That would still work, because zeros won't work this time anymore. Okay. So there's your domain. Let you guys have so much fun with the homework on that one. Let's move our way up from domain. It's something called the composition of function. Question?
So confused why it changes from the bracket to
And it's because of this right here. If I plug in a 1 into here, 1 subtract 1 will give me a 0. 1 plugged in here would give me a 2 over the square root of 0. Can I have that? So I can't have a 1 in there. I can't put in the one that gives me a 0 in for the g function. Then I got myself undefined. So, cool. Alright, composition of functions. This one you probably have seen just a quick introduction of it. So if you have two functions called f and g, the composition of, it's a function that does both at the same time. Kind of quick graphic of it. Well, let's do the algebra first though. So f, this guy here, it's like a multiplication dot, but it's an open multiplication dot. Again, we're sort of running out of notations for stuff in mathematics. So we're like, okay, how can we make this look a little different? So we have this little sort of open dot, g. What we really say is we say f composed with g. That little weird circle means composed. Or you could say f of g. So sometimes people say f of g of x. Some people say f composed with g of x. But really what you have is this right here. You do the g function. Once you do the g function, you take that output and put it into the f function. Kind of quick visual to see how this happens. Notice there's two functions. I take the x value, I use the g function to get it to g of x. Then what I'll do is I'll take the f function to get it to, I'll use the f function to get it to the end. The composition function, what it does, it allows me to, instead of having this middle step right here, it allows me to go all the way to the end right away. When I had my first job in college, which was a long, long time ago, I used to work at Mervyn's, and the IT guys at Mervyn's, what they would do, they would go, it wasn't like USB drives, they were kind of weirder than that. It was kind of the first form of USB drive, if you call it. What they do, they stick this little key into the register, and it's sort of the sale prices for the next day. Their job throughout the day was to compute the sale prices and put it into a faster function. So if you take 20% off, take a $100 instant rebate off something, their job throughout the day was to make that composite function. So when they put it to the registers, it'll just compute it faster. That was about time. How can you do it faster? So we'll take a look at an example at the end here, how that looks like. Anyways, let's go for it here. Quick example here before we get to the exercise problems here. So I got f of x is x cubed. So what the f function does, it cubes everything. What the g function does, it adds 1 to everything. So what in the world is f composed with g of 1? Again, notation here. This changes into f of g of 1. We take the 1, and the g function is going to add 1 more to it. So if you put a 1 in for g, 1 plus 1 will make 2. Well, you take the output of g and you plug it into the f function. So then that 2 becomes 2 cubed. And so 2 times 2 times 2 is an 8. So you sort of see how that 1 went through a process. 1 went into the g function first. After the g function, it went into the f function. That's pretty much what it is. Let's try a problem ourselves here. So I got let f of x is equal to negative 5x. So what f function does, it multiplies by negative 5. What the g function does this time, it actually squares it and then adds 1. So your job, try it yourself here. What is f composed with g of 0 would be? And again, the reason why I do these practice problems is if you do have time before class and if you want to try it yourself, absolutely try it yourself. If you read ahead, this is the time to sort of try the problem yourself, see if you're getting it. You do have all the answers to them, to all the practice problems right before the homework exercises are given in the book. Cool. Alright, let's go for it. At least the first one here. So f composed with g of 0. Really, algebraically speaking, what that means is f of g of 0. So off to the side, you guys are sophisticated Math 15 students. You guys can do this here. 0 plugged into for g. What is the output? Yeah, 1, right? 0 squared is 1. 0 squared is 0. 0 plus 1 is a 1. So output that we get by plugging in a 0 for g gets you an output of 1. And then, again, I kind of quickly did it right there. So now we take the output of g. We're going to plug it into the f function. And 1 plugged into f means I'm going to multiply that with a negative 5, and my final answer is negative 5. Okay, good there? Let's go backwards though. What happens if you plug in first into the f function, and then after plugging into the f function, then you plug into the g function? Would that matter? Does order matter here? That's the question, really. That's you're asking. So algebraically, this means g of f of 0. Plug it in the 0 for the f function. Again, down below, if I did that, I would multiply 0 and a negative 5, and if I do that, I still get a 0. That's interesting. This one didn't actually change at all. Alright, so output for 0 is still 0. Okay, so 0 goes in for g, and 0 squared plus 1 leave me with a 1. That's kind of weird. So reversing the order actually doesn't give me the same thing. If you think about it, remember this is something called the commutative property of addition, right? We have 3 plus 4 is 7. 4 plus 3, still 7, right? For addition, we call it commutative property. It doesn't matter the order of the way I added it. Multiplication does the same, right? 3 times 4 is 12. 4 times 3 is still 12. In this case, they're not commutative in nature. Going one way doesn't necessarily mean you get the same thing going the other. So because that, we'll have to do some other stuff later on. And this is really setting us up for exponential logarithmic functions. That's kind of what this is for. So we've got a long ways to go. Introduce it, we'll keep on going. Okay. Sometimes we don't just plug in numbers though. The whole point of this, not just crunch numbers into this. The whole point of this is actually to make a function that does both of these at the same time. That's kind of what we really want to do. So let's look at an example here. Let's go back to the example problem in the textbook here. So f of x is 2x plus 1. G of x is x squared minus 3. What I want this time is I actually want to make a function that does both of these operations at the same time. So x goes in to g, and that function has to go into f. So notice what we're going to do. We're going to write it algebraically. This is f of g of x. And we're going to take the whole entire rule for the f function. I'm sorry, the g function. G function x is x squared minus 3. We're going to plug that into the f function. Alright, the f function says I take double of that and I add 1. So in this case, then I'm going to be taking double of x squared minus 3. I'm going to add 1 to it. At that point, then you're simplifying as much as you can, and you're done. But this right here does the work of both functions. Squaring something. Alright, let's do it together here. Since I'm the one messed up, I guess I should let you guys off the hook a little bit here. So, g of x is 2 minus x. I'm going to plug that into the g function. If I do that, this would be 2 times 2 minus x squared plus 1. Good there? Whole bunch better this time? Alright, and again, squaring 2 minus x squared minus 4x plus 4, that's what you would get. Again, if you wrote it backwards or forward, doesn't matter, it's still going to be the same thing there. Add 1. And 2x squared minus 8x plus 8 plus 1 makes 9, so rewriting it, there's my 9. And again, x minus 2, if you were to FOIL it out, you get something that looks like this, just so you have it on the bottom if you need to, but you get your plus x squared. Okay, so let's try this one here. So f composed with g of x. So how about if we go the other direction? G is not going to go into the f function. And if you're going to get that one correct, yes, you can compose a function with itself. That's fine. What you're really doing is you're doing the function twice. That's kind of what you're doing here. So let you guys try this one by yourself here. This one going, the g function going into the f function. So let you guys try that yourself here. Cool. Alright, I'm going to start it here. So let's see. F of g of x. So the g function, the rule for that one is 2x squared plus 1. Plug in that into the f function, which is 2 minus x. In this case, it would just be then 2 minus, and then whatever that is, 2x squared plus 1. Again, this is the easy one here. Distribute the negative into each of those here. So negative 2x squared minus 1. Combining like terms, and we got ourselves an answer. Again, that one's going to do both functions at the same time. good there. Anybody need extra time, or we got it? Alright, and the question comes up, Mr. H, can I put the 1 first and then the 2x squared in the back? Yes, you could do that. That's no problem, as long as you have the negative sign with the 2 still. So since that's a positive 1, you can move to the front, but you leave it as a positive 1. The negative 2x squared, you can move to the back, but make sure you leave it as a minus 2x squared. Okay, composing G with itself. Hopefully you guys have tried that. I'll let you guys try it yourself here. See a lot of people getting started. So give you guys a minute here, see if you guys can do that one. That one's, you gotta foil stuff out, so I'll let you guys try it here. Alright, let me start it as well here. Okay, give you a little bit more time, or are we good? I think we're ready to start. Okay, G function of, again, the G function again. The rule for it is 2x squared plus 1. So we're going to take that guy and plug it into itself. This kind of looks weird at first. You get used to it after a little while here. So that means I'm going to have a 2. There's my variable. But my variable now is 2x squared plus 1. And I need to square it still. I'm going to have to add 1 to it. So notice it's a function within a function. Alright, yes, we've got to multiply all that out. So 2x squared plus 1 squared. Again, doing it the faster way here. I said, Mr. H, what's the faster way? The faster way is you take this first term and you square it. So 2x squared gives you 4x to the 4th. Then what we do is you multiply the two terms together. So 2x squared times 1. And then you double it. You multiply it by 2. Because you always get doubles whenever you FOIL out a binomial with the same numbers here. And then you take the last term and you square that one. So 1 squared is a 1. Alright, distribute the 2 makes an 8. X to the 4th, 8x squared. A 2 plus 1. Eventually you get yourself a 3 at the end. And done. We're good there. Maybe, sometimes. And hopefully we're trying it as well. Okay, next. So, just quickly raise your hands. How many have seen that before in intermediate algebra? 1, 2, 3, 4. 4. Okay. 5. Okay. All right, let's go over it. We're going to dig a little deeper here. So this one I don't think you've actually did in intermediate algebra here. We're going to look at the domain of the composition of the function. So if I take an arbitrary functions here, what do I know without actually even doing the process? What do I know what the domain's going to look like? Alright, in your book, on page 262, it actually shows it to you. Again, I'm not going to repeat this process. I'm going to show you a different way, because this shows you one way. I'm going to try to show you a different way here. I don't like the whole fact that it says, oh, you can't figure out the denominator here, so this is what you have, and then from there you take one piece, and then you have to actually then plug it into the other one. So there's this whole thing of plugging stuff into multiple directions, and you sort of don't see where it comes from here. I'm going to try it my way, and this should be hopefully a little better. So let's try it this way here. Once you get doing compositions, they work real quickly. And so then once you put a fraction or a function together, you can kind of see where the pieces are coming from, where each of the domains have to come from. So let's go with it. Let's do practice problem number 5 together here. So I need to know the domain of f composed with g. That's what I need to know. Okay, so what I'm going to quickly set it up, but I'm not going to simplify. So f composed with g really is f of g of x. The g of x is this guy here, which is 2 over x minus 3. And I'm going to plug that into the square root function. So the square root of, and again, that x now has changed into 2 over x minus 3, plus 1 at the end. Everybody okay there so far? Hopefully, sometimes, maybe. Okay, so just a little disclaimer here. When you look at this, most of the time when you look at the bigger one, the domain of the smaller problem is already going to be in there. So let me repeat that so it kind of makes sense. When you look at the bigger expression, usually the smaller domain issue is already in it, but not always. So we sort of handle the smaller one and we move out to the bigger one. So first of all, if I see this, I see the big square root, then I see a fraction here. So my fraction is the one I'm going to focus on. It's the smaller problem. Because of this fraction here, what can x not be? Can't be a 3. We good? Because if that is the case, then I'll have a 0 on the bottom here. It'd be 2 over 0. That's a problem. So one domain restriction is because of the fraction. Then we look at the bigger problem. The other issue is that square root. So then I know this right here off to the side. I know that this piece has to be greater than or equal to 0. So I then rewrite it over here. 2 over x minus 3 plus 1 has to be greater than or equal to 0. I start solving this one. Keep in mind, this is my first problem. My first problem was the positive 3. So now let's start solving this guy. And I had actually had to thumb through the first chapter of the textbook in chapter P. Remember that one, the preparatory chapter? That's the one thing that's missing. We actually did not... No, we did these ones. We didn't do square roots in here. Okay, so we did this one here. So how do we solve this? According to chapter P, or the preparatory chapter, we get common denominators. We want to make it into one single rational expression. And then we're going to compare it to 0. Remember that? Write it as a single rational expression. I have common denominators now, so it's x minus 3. Let's see, on top it's x. 2 plus a negative 3 is a minus 1. And again, that's still greater than or equal to 0. Okay, so that's technically what we're solving. We're solving when that happens. So remember how we set up a little number line? Remember how we take test points? We found out if it was true and false? All that good stuff here. So first things first. Since I'm running out of space here, I didn't rewrite all the pieces here. But first of all, what's the problem right here? Still 3, huh? So when I do my number line across right here, I'm going to go locate 3 and I'm going to put an open dot over there. And again, which is what I was telling you right over here. The smaller problem is still an issue over here. So the not being equal to 3 has already been taken care of because of this problem here. But remember when we did this, we set actually x minus 1 equal to 0. So if you set x minus 1 down here somewhere, x minus 1 equals 0, when does that happen? At x equals 1. So we're going to put a 1 over here, but this time we're going to put a closed dot. So you guys remember when we did this in chapter P, we picked test points. We need a test point lower than 1. We need a test point between 1 and 3. And we need a test point higher than 3. And we're going to compare it. You can do the original function if you like, or you could do this one right over here, comparing it to 0. I like comparing it to 0. Alright, let's go for it. Let's test 0 real quick here. 0 is less than 1? If I plug in a 0 here and 0 here, is this true?
Yes.
Yeah, it'd be a negative 1 over negative 3. Negatives cancel, leaving you with a positive 1/3 greater than or equal to 0. That's true, so I put a little t up here. Well, that's okay, let's test 2 here. So, x equal 2, true or false?
False.
Yep, 2 minus 1 is a 1, and 2 minus 3 is a negative 1, so that makes a negative 1. No, that's false. Cool, and then pick something bigger than 3. Bless you, bless you. 4 is good, yep, 4 minus 1 is a 3. 4 minus 3 is a 1, and that is true. Okay, so what do we got here? Remember, the little problem was already taken care of by the big problem. Not always does it happen, but in this case it did. Final answer?
Negative infinity to 1 in the bracket.
Perfect, yep. In this one, are we including it? Yes, we're including it because of the greater than or equal to symbol. Bracket, union, not including the 3 because not part of our domain, and going off to infinity. There's my domain. Again, this is my domain for the composition of f and g. Okay. It's already the composed function together. I think you guys can probably do the next one here by yourself here. Practice problem number 6, very similar here, except now I have 2 square roots. Again, an unusual one. Maybe just go as far as you can, as far as you feel comfortable. Stop there, and I'll sort of fill in the gaps here as we go. It's an interesting one here a little bit. Alright, let's go for the f composed with g, f of g of x. Alright, so let's write the function together. So g is the square root of 4 minus x squared. So square root of 4 minus x squared. That's going to go into the f function, which is square root of x minus 1. So square root of the variable itself minus 1. Okay, so again, 2 problems. The little problem and the big problem. The little problem is this one right here, is that right? 4 minus x squared? And the bigger problem is the other square root. It's this whole entire piece right here then. So let's take care of the little problem first here. First of all, 4 minus x squared has to be greater than or equal to 0 because of the square root property. Two different ways to do this here. I'll probably do this here. I'll probably multiply through by -1 because I like to be able to factor if I can. Remember, if I do multiply through by -1, I have to switch that inequality around. Cool. Okay, how do we solve this? Got a little small problem. I can solve individual linear inequalities, but in order to solve a quadratic inequality, what I would have to do, set equal to 0, and solve it and figure out when it does equal 0. Can't give you the answers yet. This one's a long one here. I'll just tell you ahead of time ready here. So x, let's see, x squared minus 4 would be x plus 2x minus 2. So on our number line, I got a positive 2 and negative 2. They're both filled in dots. They're both closed dots. Now the question is, where is it true? Let's see. So again, we go back to this port right here. It's before we change it to an equal sign. So a number that's a little less than -2, maybe -5. -5 squared is 25. 25 subtract 4 is not less than 0, so that is a false statement. Plug a 0 in. 0 into that makes it -4. -4 is less than or equal to 0. That's a true statement. And again, a positive 5 will do the same thing. So our little problem is the domain is from -2 to +2 inclusive. So -2 to +2 brackets on each side. Good there? Little problem. Now let's handle the bigger problem here. Yep.
There's like another small problem though. You haven't messed around the sign-in sheet.
That's a good thing. Okay. The other small problem to be taken care of is I'm going to pass out the sign sheet. Thank you for that. All right, let's go for it. The big problem now. It's this piece here. It's the stuff that's inside the big square root symbol here. So I'm going to write on the next slide here. It's the square root of 4 minus x squared minus 1 greater than or equal to 0. That has to be greater than or equal to 0. All right, and with this one, let's go for it here. Square root here. I'm going to add 1 to both sides. Leave me with this on the one hand and 1 on the other. Okay, and this one, let's talk about it because we didn't see this in chapter P. It doesn't really come up in algebra context with the square root and an inequality. The only way I can still solve this and still keep on solving it, the only way I can square both sides right here is if, first of all, this guy is positive, because I can't do it with a negative number. Second is, I already have a domain restriction right here. If I don't have a domain restriction here, I wouldn't be able to do it. I already figured out when 4 minus x squared is greater than or equal to 0. So we'll talk about it in the next problem as well here. Okay, if I do that, I square both sides. It gives me 4 minus x squared greater than or equal to 1. Let's see what I do here. I'm going to subtract 4 from both sides, leaving us -3. I'm going to multiply through by -1. And again, I have to switch the inequality, and I'm left with a 3. I guess I could have subtracted 1 from both there. And I'm stuck again because of this little x squared. The little x squared means I have to shift these 3 over to the other side. Using that comparison, set equal to 0 and factor. And the question is, can I factor this down? So if you want to, you can use the quadratic formula, or you can do this little sneaky way of factoring. Let me show you the sneaky way of factoring. Since it's just a binomial, since it is a square, since there's a minus sign right here, the factored form of this guy is x plus the square root of 3 and x minus square root of 3. Isn't that still, will that still give me the same thing? I know, pretty sneaky, but it works. Again, if you didn't want to, you could use the quadratic formula. Still would have given you an answer of plus or minus root 3. But if you just have a binomial, remember how we always need this to be a perfect square? You technically don't. You just need to figure out numbers that multiply to give you that number. In this case, it has to be the same number, so you just really take the square root of that number. If this was a 4, you take a square root of 4, which is 2. This is a 9, you would have done that the same. So, alright, the two answers I got is negative root 3 and a positive root 3. There's my end values. What did I get here? I just got this right here with closed dots. Alright, if that's the case, again, testing this one over here. If something less than negative root 3, anyways, what's approximation for root 3 anyways? Anybody?
1.7.
Cool, okay. 1.7, 1.73, somewhere in that range. 1.72, okay, cool. So 1.7, so anything less than 1.7, I could put a 2 in here. A negative 2 squared is a 4. 4 minus 3 is a 1, and that is a false statement. I guess I can do it around here. So false. Okay, between negative root 3 and a positive root 3, pick a 0 here probably. 0 plugged in, true or false? True. And then plug a number that's bigger than root 3. Again, 10 would be great, right? So that's still bigger. 10 squared is 100, subtract 3 is 97, and of course that's going to be false. Alright, so I have this. Finally got to it, so this is a bracket, negative root 3, positive root 3. Whew. So my little problem was from negative 2 to 2. Right, my bigger problem is from negative root 3 to positive root 3. Now the question is, which one do I take? Again, it's the intersection of the two. So if you go back to the beginning, that's what I have first. To solve the smaller problem, this is what I have to solve the bigger problem. Again, where's the intersection between the two? Yep, not the negative root, not the negative 2. It's actually this. It's the smaller band right here, because remember root 3 is about 1.7. So the final answer is this right here. It's the one that's the smaller band. That's where the intersection occurs. But of course, for those that read ahead, said, Mr. H, this is cinchy. I wish you could go like twice as fast, Mr. H, because it's too easy. All right. Give me 1 second here with something. We just did F composed with G. You guys get this one right here. G composed with F. Alright, let you guys start it. Give you a minute here. And looking at time here, I think we will be able to finish up here. This is 6. We need to go to 9. So we got 3 more to go. Alright, give you guys a minute. Try it yourself here. G composed with F. We just did F composed with G. again, just so make sure we have enough time here. I'm going to start it just sort of slowly. If you're working ahead of me, keep on going. But B, G composed with F. Just keep on going. If you're sort of confident that you're doing it correctly, keep on going. Look up every so often, just to make sure you're good in the same track here. But let's go for it together. Those are waiting for me, since I see quite a few guys waiting for me. Okay, G composed with F. We take the F function, which is the square root of x minus 1, and we're going to take it into G function. So if I do that, then it looks sort of like this. Remember, because the G function is just square root of 4 minus x. It's x squared, huh? Okay. Put that in. This being squared, right? Like that? Alright, before we do anything else, again, before we even simplify that right there, we look at this and say, what can x not be? Well, it's a square root, right? So x minus everybody good there? That's the small problem. There's my solution to the small problem. Alright, the big problem is 4 minus the square of the square root of x minus 1. That has to be greater than or equal to 0. Well, I'm so grateful that little square is there. Because if you take the square root of something and you square something, what happens to it? It cancels. So kind of careful here though. It's not x minus 1 because you have this little parenthesis right here, right? You have that. So then you have the negative just sort of moving in or distributing to the x, distributing to the... Hey, cool, we got ourselves a linear function. None of that weird stuff that we did for a. 4 plus 1 is 5, so we have something that looks like this. Oh, sorry. Go back real quickly here. That's on this side still. Plus 5 greater than or equal to 0. I'm running out of room here, so I'm going to bring it up here. So at this point, how about subtract 5 from both sides? Divide through by negative 1. And again, I have to switch the inequality around, and there it is. So let's see if this makes sense here. Let's see. I need numbers that are greater than or equal to 1. I also need numbers because of the big problem that is less than or equal to 5. Notice, this one did not take care of this issue here, right? The big problem did not contain the small problem within it this time. But what's the intersection between these guys? Bless you. I need numbers bigger than or equal to 1. I need numbers that are equal to or less than 5. So the final answer is something looks like this, right? The only numbers I can use are actually 1 to 5. That's it for this particular function. Okay, good there. Let's go a slightly different way. Let's slightly sort of go backwards here. Alright, this is called the decomposition of a function or decomposing a function. In calculus, when you guys get there, you guys will do this because you want to fit stuff into a formula. And depending on the formula you want to fit it into, the functions actually could be different from one another. So let's go through this example here, and then we'll do the practice problem here. Somewhat easy when you look at it here, but let's go for it here. So notice when you look at this problem, you have the 1 over something on the bottom. That's something that is the square root of 2x squared plus 1. The question is, what two functions f and g is this made from? So this is already the h function is already a composition of these two. But the question is, what are these guys made from? So you're given one function, and then you want to create the other function. So the g function is 2x squared plus 1. What would be the f of x function if that's the case? Yeah, so notice everything is taken care of. This whole entire piece right here becomes the variable. So then in this case, if this becomes g of x, then f of x is really going to be 1 over the square root of x. X, that whole thing just becomes the variable. Now, does it always have to be this way? And so what they said is, they said, okay, then try it out just to make sure it does it. And then again, you try it out. But it doesn't have to be that. The g function could be slightly different. The g function could have just been x squared. The g function could have just been 2x squared. So for practice problem number 7, it says repeat the problem and let g of x actually be the square root of 2x squared plus 1. What is f of x? Don't say it out loud. Think about it. See what you guys say. Give you guys like a whole 10 seconds. Okay, time's up. Nope. Let me go back to this one because it will make sense here. This is your composed function. G of x is the square root of 2x squared plus 1, right? So f of x would be just this whole denominator went away, right? Yeah, the same one, yeah. There's still h of x. That's right, I should probably write it in here. That'd be good to write in here. So again, h of x, the composed function already was 1 over the square root of 2x squared plus 1. Thank you so much. And since the g function really took the whole entire denominator. So really the whole entire denominator just becomes the variable. So 1 over x. Again, this stuff is used. What happens in, it's called second semester calculus. It's called antiderivatives. There is literally 100 formulas there, as we've made to go from antiderivative to the function itself. And so what you have to do is you have to somehow fit this into that little formula. And if you can fit it, then you can take the antiderivative of it. And if you can't fit it into that, then you can't. So you're going to try to sort of fit a formula like this. So if this right here, 1 over x, if I know this formula as an antiderivative, g of x is going to be this function for me. And then I can take the antiderivative of 1 over x easily. So that's kind of where it comes from. Okay, but let's finish up here. Let's do some two example problems of this stuff here. Where does composition of functions work? When do they work? How do they work here? So oil is spilled from a tanker in the Pacific Ocean. Area of oil spill is perfect circle. The radius of the oil slick increases at a rate of 2 miles per hour. So as they see it on the satellite image, they can kind of tell like, oh boy, this is getting bigger and bigger. First of all, express the area of the oil slick as a function of time. So notice we got the radius only, right? We have the radius, but then I want it in terms of time. Calculate the area covered by the oil slick in 6 hours. So let's go for it. Let's see, just go through the example problem here. So the area of the oil slick, we know the area. That's a formula from geometry, right? Pi r squared. But since the radius is increasing in terms of time, it's increasing at 2 miles per hour, r actually itself has a formula to it, which is 2 times x. And so what we do is we take the r formula into the area formula. Kind of looks like this. The area now is f of g of t. The g of t is the 2t. And notice what we do is we create a formula now of the area just in terms of time only. Once we do that, we plug it in. Again, for b, substitute what happens in 6 hours. We just plug the 6 in for the t value this time, because now we got everything in terms of t. And we get ourselves 144 pi square miles. Okay, let's take a look at ours here. Practice problem number 8. What would result from example 8 if the radius of the oil slick increased at a rate of 3 miles per hour? Again, go for it. Give you guys a minute, try it yourself here. We'll have just enough time to finish off the other problem. And again, give you guys a minute here. So first thing, can you make the area in terms of time only? That's A. And second, what happens after 6 hours? And according to the picture here, if you read ahead, you will gain muscles. Maybe not so much in the chest area, but maybe like in the head area. But it's close enough, you know. Thank you. The sign-in sheet almost like needs to be passed twice around, you know, just for everybody to see it. Okay, let's go for it here. So, area formula. I'm going to kind of do it just like the textbook. You can skip, if you like, here's a pi r squared. We got the radius formula because it's in terms of 3 miles per hour, we get ourselves 3t. And we're going to plug one into the other. So area is going to be f of the g of the t function. And again, why we say f and r? Because r is the variable for the f function. Why do we say g of t? Because t, the time, is the variable of the g function. And this just so it looks a little closer to what we've studied before. So let's go for it here. So we're going to plug in 3t into our f function, becomes 3t being squared times pi, or 9 pi t squared. So now we have a form of the oil slick based upon the just time only. Kind of interesting. Remember the BP oil spill that happened like 3 years ago or something like that? Now it's interesting because still oil is a natural product in a sense, right? Because they haven't refined it any. So they find out that there is now new ocean life in that area, and they actually are eating up the oil. It's kind of weird how that sort of all happened there, because they were initially surprised by where did the oil go, because after 6 months worth of cleaning up, there should have been more oil, and they found out that seawater diluted it, and the sea life there actually was using it in some symbiotic relationship. That was kind of interesting. Okay, and after 6 hours, all we do is plug in a 6 in for the t at this point. We get ourselves 36 times 9, or 324p, and again, it's in miles squared. Okay, and what we start off in the beginning of the class is the whole point of discount, or how do you get a discount, and then how do you get a percent off or a sale price. How does this work? It says a car dealer offers an 8% discount off a manufacturer's suggested retail price, which you see on cars. At the same time, the manufacturer is offering a $4,000 rebate on the purchase of the car. Question: does it matter which one goes first? If I take the 8% off the sale price and then take the $4,000 off, or should I take the $4,000 off and then? Cool. Okay. So write the function r of x that represents the rebate. Then let's d of x would represent the discount, and then we're going to do each of these here. Rate the rebate of the discount, and then we're going to do the discount of the rebate price, and we're going to compare the two. Cool. Let's go for it. So everybody okay with this one here? The rebate is $4,000 off, so it's the price of the car minus $4,000. That's easy enough. The discount, now a little tricky. Whenever you get a discount, since 8% off, isn't it just, it's taken away from something before it, right? So it's 8% of that something. So the way you calculate discount is you put an x over here, and then you subtract off a decimal point of that x. So if you think about it, 8% discount, are they really paying 92% of the sale price? That's kind of where the 0.92 comes from. Okay, cool. And then the first part here is rebate of the discount. Again, plug it in the discount into the rebate function and it gives you this. So it's 0.92x subtract the 4,000. Doing it the other way, now the rebate comes in first, and it's the 0.92 of the x minus 4,000, and we get something that looks like this. First question, are they the same? They're not the same. That's kind of weird. Okay. So let's see. This one I'm knocking off $4,000. This one I'm only knocking off $36.80. So at this point in the equation, as you subtract the 2, you find that this equation shows that it will cost $320 more for any car regardless of its price if you apply the rebate first, then the discount. Why so? Because if you apply the rebate first, yeah, you're taking the 8% of the rebate, in a sense, away, because you're applying that first, as opposed to if you did it later. Anyways, one problem with us with 5 minutes left here. Our problem is this: we have a 6% discount and we have a $4,500 rebate. Can you write for me the R of x function real quickly here? We'll do it by pieces here real quick here. So give me R of x. What's the rebate function? That sounds good by me. It's x minus 4,500. That's this piece right here. The discount of x, again, that's still, since we're getting a 6% discount, we actually are going to pay how much percent of the original price? 94. So x minus 6% gives you 94 of the original price. And again, computing this one, I don't know if you want to do it here, later, that's fine. Rebate of the discount of the price gives us, plugging that into the rebate. So we get $94 off, and then the 4,500. Doing it the other way, sorry if you guys want to see that there. A couple of people writing it out. Ah, there you go. That's fine. So if you're at a dealership and they take off the rebate first, I had it in my mind here. So a car that costs $10,000, you take the rebate, now it's only $5,500, and then you're going to pay 95% of that, right? You still get the full rebate there. You still get the full $4,500. If you take the 6% off, you're looking at a car that's $6,000, right? Because it'll be 95%. So a $10,000 car now costs $6,000, and then you take the rebate later. You get a little bit less of a rebate on it. All right. Anyways, going the other way here. Discount of the rebate of the price. Again, this is just sort of more practice with it, if anything here. And if that's the case, you only get $42.30 for the rebate itself, and if you subtract the 2, you find out that you're going to pay an extra $230 if the rebate is applied first. Alright, and we finally made it to the end here. Okay, so Thursday's class, try to read ahead. I'm going to go a little bit faster in lecture for 2.9. I'm going to try to finish in an hour. And we're going to sort of just do the highlights in 2.9, just real quick. And then, so hopefully that gives us an hour for homework or any homework questions. I'll pass out the study guide as well. All right.